it's as we spoke before. It just has magic happen. It's just main of the topological part. So it's Marco and Quentin, and it's based on HKM. So basically, throw away a few of their moves, and so we prove that any even surface in the above sense admit such a diagram, which is called bounded unlink diagram. And if you have two such surfaces, you represent each of them by some bounded unlink diagram, then you can pass from one to another by a sequence of the following moves. So the one set of moves, it's so-called band slides. So you have here one band, you attach here, and then you slide it over here to the other side. So this is one move. The other move, it's still sliding, but now if you have your green part, so you have two or one handle here, then you can, so it's enough to do it only for two handles actually. Then you can slide like this, so you can slide bands over two handles. And then another thing, it's again, so if you have such a thing, you have here and here, you have either or that one. Then this is the same as if you have, and you slide over. So sliding under and sliding over is the same. So this move is called swim. This is called band slide. So they are basically both band slides. This is also band slide. And then the usual Kirby moves, which I already introduced, so they are always there. Okay, so these are the additional moves. So
sorry, I don't understand the swim move. What?
The swim move?
It's an isotopy, isn't it?
Yeah, this is an isotopy. Yeah.
Oh, it's for diagrams that you are describing this.
Exactly, it's for the diagram. It's exactly. It's so it could be, or even intersection. You can go through and pass on the other side, and it doesn't matter whether you do it over or under.
Sorry, can I ask one question? So the HKM diagram you draw, so the green parts actually diagram in S3, right, in the boundary. So, but from what I understood, the white part and the red part are actually in the 4D. So how should I understand this?
Can we discuss it later? So the diagram leaves, so you can think about the diagram in S3. Okay, and so now clearly I would like to construct invariants under of these pairs, which doesn't change under these moves. And for this, you start with unimodular category. Any problem? So unimodular even category. So meaning this is braid modular category with additional given structure. Unimodular means that projective cover of the tensor unit is self-dual. So, and this category, so I will not properly define for algebra objects and so on. So, but so I will need, so I assume everybody heard already who is an algebra object in such a category. And I will need a Frobenius algebra object. In this category. And then I will need another object, which is F module. So F module meaning that I can make sense of the following diagram. So if I have this identity morphism of V, and if I have this Frobenius algebra back on this, then there is a morphism from F tensor V to V. This is a left action on V, and it's induced also a right action on V star by doing just that. Okay, so there is so automatic, so any such dual of it comes. So I am allowed to do duals because I'm Riemann, everything is pivotal, all good here. Okay, and then I just wanted to recall you that in 21, together with Marco, we constructed invariants of these four-dimensional Handel bodies with values in these unimodular even categories, and this goes by using this algebraic construction, which tells us that these OHBs actually can be extremely nicely described in algebraic terms. So it's basically just a category which is generated by so-called what we now call BP Hopf algebra. So BP is for Bobchio-Pergolini, and this is generating object. This is basically the one object. So any other object is just tensor powers of this one. So for any such functor is just completely defined if I tell you where this guy goes here. And the universal object here, as we learned yesterday from Marco, it's the end. So you just send this H to this end, and you're completely happy with this end. We also proved it has also whole structure, this BP Hopf algebra. This provides you with invariance. Each time you give me such a category, you have invariant of this body. And this end is a Hopf algebra. And so this means that it's equipped with multiplication, co-multiplication, unit, co-unit, this S. And what is Bobchio-Pergolini in addition requires, it has an integral. This is what Marco didn't explain last time. This was the reason why he removes it was component from these constructions. It will come probably on Friday. So you need also integral, which is an element in this H bar or epsilon star. It's a form on this epsilon. And this is an element in epsilon, central element with some properties. And basically this thing, so you use this form to evaluate two handles, and you use this guy for one handles. So these are two elements which are important. So these are integral. So basically I don't have time to explain what's integral, just ask me later. This is so-called co-integral, and they are both there to define things, to define invariants for exactly for this QB, for this green part of my diagram. Okay, and then I still need to adapt this construction to define something for the
question. Is not self-dual the connection? If PP is self-dual, right? If you take the dual,
so it has such which is Hopf pairing defines kind of self. It's self-dual. It's self-dual by definition. By definition, just. Exactly. So you have this co-evaluation which is given by hopefully, but you require this to be not factorizable otherwise. Okay. Okay. And now so clearly I just need to define who are these attached bands and who are this white and red stuff in my pictures. And this right, and so this stuff is defined by saying that so this guy will send in my diagrams just to the action of F on my V, which I have chosen. And that basically that's it. And now, in order this action satisfies these moves, I need to define something which I'll call a banded unlink pair. And so the definition is that this my pair of objects. One is the Frobenius algebra, and the other is the object, the F module. So they build a banded unlink pair if following is satisfied. So if I take my Frobenius algebra and act here on the module V, so this is my V, this is my V, so I will do it this way. Then this is the same as identity on V. And the second property is some, so it's basically it's useful to introduce this morphism to call it B. And the first property says that the partial trace of this morphism is identity. The partial trace on this component.
Yeah, Frobenius algebra is red.
Exactly, Frobenius
And
algebra.
the vertices is the action.
This is F.
Vertices is action.
This is morphism from B star B to V star V to endomorphism of V star B. I can take a partial trace here, and I require that this is identity on V. This is this property. And the second property tells me that basically it tells me exactly this, that I can slide red and I can slide over or under, which tells me that this morphism B is and transparent. So component colored by lambda should slide, and F transparent band should slide. Because this is the same as saying, so if I go here under, then this is the same as just, so this is just saying it's transparent. So basically this is the two conditions which I need, and they all consist. So only thing you have to look at is this endomorphism of B star B. Which, so here clearly what does it mean? It just I have this so in terms of Frobenius algebra, so this is the action, this is identity co-multiplication.
Oh, okay.
So this is the diagram in terms of the Frobenius algebra. Okay. And
What was curly F? It's a F.
Only F Frobenius algebra.
Frobenius algebra.
It's also straight F.
It's the
It's
same.
the same. Oh, sorry. It's a straight. Yeah. It was only E was curly. Okay. And then the theorem, which I don't want to write, but it's also our main theorem. Each time you have unimodular category, you have a banded unlink pair of Frobenius algebra module, you have invariants of sigma and D. Yeah. And so it's straightforward. You're just checking these moves, and it's basically all the moves encoded into this thing. So not a big deal. The only big deal are to find interesting examples. So I can provide basically. So after we didn't find zero, so we were looking at a lot of paper by very smart people constructing a lot of interesting Frobenius algebras. And what we realized that all these Frobenius algebras, they basically boil down to the following example. So most of them boil down to the following. So your Frobenius algebra is just a following thing. So you take just any object in C, and you consider X tensor X2, which is a canonical Frobenius algebra with the following Frobenius structure. So the action exactly, I should tell you who is a module V. So V would be a guy who is X times Y. And then such an action would be, so it would be just, so you put here X star. So you put here X, Y, and you just connect them, and then you have this X and Y, X star. X. So that's it. So this is the action. And the coaction is this dual, it's clear. And then this morphism B, it will look just like as follows. So if you have here your Y and Y, they will survive on the left and the right. So probably one will be dual. And then here it will be X star X. X star X. So this is just this. And now if you in addition require that your Y is transparent, this quantum dimension 1, then you have all the conditions. And this is an example. So there are many things which run like this, which usually formulated much more complicated than what I'm doing here, but they are at the end they boil down to such a thing. And so why I'm not so excited about this? It's because so each time when my morphism like this, it just factorizes. So the easiest case you can imagine that B is transparent is the case where instead of this B, so this B will boil down to something which is like that. And this would mean, so for your surface, if you think about, so your surface, so what is the boundary of my surface here? The boundary of my surface will be, so this is my band, which I attach to my unlinks. This is my unlinks. And the boundary of my surface will go exactly like this, here and there. And here it will like this, here and there. This is the boundary of my surface. This means that the whole structure, actually what we defined it boils down to invariance of links on the boundary of the 4-dimensional, which we had already in any, so just take Richter-Drive factor, you have them always, you always comes with. And so the challenge is to find something which does not have such property. So for example, any interesting Y here. So if you're not factorizable, any interesting Y here, which is still perhaps not completely transparent, but still E and F transparent would be, so it would be a great example, which we are looking for. So if somebody has something like this, it would be great. And then in the remaining 2 minutes, so actually we started to work on this because we thought our main example is just the end itself. So because you know the end has also canonical Frobenius algebra structure. So not canonical, but it has even 2 different, but it's always a Frobenius structure. And so for this, basically, so we wrote down these things. So Marco wrote it down. So we wrote the second construction of invariants, which actually modify the usage of this pair, which we usually use for 4-dimensional invariants, by modifying them. And instead, we're using another form and another central element here. And this form phi, you actually obtain from the integral by shifting it with the central element z, which is so-called Henning central element, which satisfies this condition. So this is equivalent of the definition of, so this is Henning central element. So you also need to have that this is central, and you need that it's as invariant. And then this property will guarantees you again the sliding of 2 handles over 2 handles. So you could evaluate 2 handles with something which is slightly more complicated than just integral. And you can also find a form for your bounded unlink, which will be psi some condition on this form. So each time you have interesting solution of this guy, you can again construct invariant of the sigma and W, which is so again, so if you just, so the example here would be, so the example would be this z is equal to 1, and omega is equal to co-integral. Then you're back to the situation we considered before. But in this language, it's the second construction, so your coend will be an example. So basically, you color everything by two handles, and again, you get something which is boils down to the boundary. And so the only cases which could be interesting is to find new. Exactly, perhaps I should write that this z double product should be the co-integral. So it should be, this is also central element, this is form, this is also form, this is the element, and they satisfy this condition. And
Yeah, another solution is z equal co-integral, right?
Exactly. Then from the
But
beginning,
then-
everything is trivial. Exactly.
Everything's trivial.
So we know a few solutions. I think 4 solutions we know. So
But do you know some nice, interesting solutions?
this is what I wanted to ask the audience.
Yeah.
So any interesting
course.
solutions. So basically, I can also give you abundant and unlink diagram exactly for these two guys. And this is so in this setting we don't know anything about this new invariant. So for example, for 4D handle bodies, we know if we are semi-simple, nothing interesting happens. We don't see, we're always on the boundary. So here you can even forget the part so you can forget about 4D handle body. You can just say, okay, so so my dream would be to distinguish these two with some hope algebra. So this would be so absolutely. I can draw you
So
diagrams.
this is like what? This is a diagram for ribbon surfaces, or?
These are two surfaces, which one of them is a smooth disk and the other is topological disk. So they are distinguished by some homomorphism. So I can draw you a diagram. I can immediately draw, or you can ask me to draw in the questions. I can draw it. It's really easy very easy. Unbounded without any green part, so it's easier than what is drawn over there. And if you can provide any Frobenius algebra, which Frobenius algebra and Frobenius module in a braided monoidal category, which would distinguish these two, it would be a great breakthrough.
Sorry, you're saying that one of the two surfaces is not a smooth disk, am I right?
Exactly.
So it cannot be drawn as a banded. All your banded stuff is smooth surfaces, aren't they?
Wait a sec. So you can draw the diagram which are admissible for both of them. But it's a good question. So in which sense? It's flat. No, it's no. They're both smooth, but they're still exactly because Quantum homology is also smooth. Sorry. They're exotically noted. This is what they say. Yeah, they're both smooth. Thank you. But you can distinguish them by invariant. So Quantum homology is smooth invariant as well. So what I wanted to say, perhaps. So I don't know. You can ask me. So why I dropped this one. So because like very recently Lee and Yetter claimed that so this is unfollowed cork, and the cork is obtained by, so basically you see these are two components. This is this 4-dimensional manifold obtained by or 4-dimensional two-handle body with one handle and one two-handle. You see they are both unknots. So you see this is, you can remove this right minus the 1, 3 right minus the 1, and this is the unknot. And you get interesting transformation between two such guys if you put this dot on the other side. So basically, so for example, if you put a disk here, so if you put so this should be green, this all should be green, and then I put my disk like this, and then I do this hyperelliptic transformation, which would put this dot on the other component, and these two guys were considering very similar constructions I'm suggesting. So they for closed surfaces, so they computed invariant of this diagram where this is on one component and another diagram where this is on this component. And they were working in graded vector spaces. So their Hopf algebra was exactly what Sarah was talking about, Z mod LZ for some L. So, and they were claiming they distinguish this absolute quarks with this Hopf algebra. So this was the result in the paper at the end. So in the published version, I think it's not the version which you have in the archive, but in the published version. And this is just mistake because you cannot use, so exactly for this quarks, you cannot use this technique because this one is not the banded unlink diagram. So even if they represent disk, both that one represent and that one, you cannot use this technology because you need additional moves if you're going out of this unlink diagram. So topologically, you would slide this guy and you would, yeah, but this sliding is not existing in this set of moves. So therefore, so it was just a mistake. So it's really, there is no one single example where something exotic was seen with this technique. So this is a pity. Okay.
Okay, thank you, Anna.
Do you know if something special happens, if the Frobenius algebra has some special properties, say it's separable or something like that?
So the only thing which I can say here is that it's important to have enough transparency. So it should be sufficiently transparent. So for example, so also what we were stuck with that many people so thinking about very famous fancy Frobenius algebra, but usually it's hard to provide modules over them. And then you're taking as D the same as F. And then this condition will immediately tell you this B, so the Frobenius algebra itself should be transparent.
Mm-hmm.
You just you take this B, use one's Frobenius relation, you see that F itself should be transparent, and this probably would not produce interesting invariants. Yeah. So basically, you forget about bands. Yeah. So therefore, yeah, it should be enough transparent, but somehow this F should be special in the sense it itself should be not transparent, but should admit some other object which are F transparent.
There are other questions? So I have a comment, but like this algebra, this F is Morita equivalent to tensor unit, trivial algebra.
Yeah, exactly.
Morita equivalent to, up to Morita equivalence, it's just trivial algebra. But I guess one can find, maybe look at less trivial algebras.
So exactly.
I mean, from module categories, actually. So basically this algebra corresponds to a regular module category. And from other nice module category, I mean, there are other nice exact module categories.
I would be very happy if you provide.
They provide less trivial, which are not equivalent to identity.
Great, but then I need also a module.
Yeah, yes.
And then I need this property.
Yes. Just,
and
but
yeah,
was just, of course, it doesn't work because it's trivial algebra.
Yeah. Sure, but this is, for example, so where we found this was this Lieta paper. So this is how they constructed this exactly with this thing, and with graded vector space.
Yeah, I think one should look at module categories.
Yeah. Look at pivotal module categories. Pick any object in a pivotal module category. Look at the inner end. It is a Frobenius algebra, and the object you've chosen to start with is a module.
Which module over what?
A module category in the sense that you have a category which behaves over the monoidal category as a module behaves over ring.
Yeah, but more concretely, so
like examples.
So what are examples?
I mean, quantum SL2, small quantum SL2. What are pivotal module categories? Can you give me one?
Shimizu has a recent paper.
Yeah, okay. He classifies pivotal or he classifies exact? Exact.
He has two papers. One is in preparation, and the next will be pivotal.
Ah, okay.
Yeah.
So I should wait for this paper to appear.
But for example, the class of interesting module categories, and it's continuum variety of so-called exact module categories. So some of them will produce nice, I mean, very non-trivial Frobenius algebras.
Let us discuss this. Yeah.
The problem is that it has to be E-transparent, right?
Yeah, no, but this is yes.
Exactly. So it's so the latest condition. So it was also so condition 1 is actually also very so if you would like to take any, for example, the one, so we had it also with modified trace and like with Steinberg. And Steinberg is the only V which you can put for the end. Otherwise, you would not have 1. So it's not only 2, it's also 1, so which is very restrictive.
Yeah, you're asking a lot.
But I'm very open for anything.
Good.
Okay.
If no more questions, thank you, Anna, again for a nice lecture. Maybe we make a little break.
Yeah, sure.
Like 10 minutes break, yeah?
Yes, I think it's always good.